Okay, so we did our lab yesterday on velocity, or sorry, on position versus time graphs. Something I need to tell you, because I realized I forgot to mention this. When you are doing your variables, you must have 3 controlled variables. I only mentioned 1 in class yesterday, okay? So you must have in your lab report 3 controlled variables identified and explained. All right, so we already talked about one of them, okay, but you guys need to kind of look at the system there and look for anything else that could affect the speed of the cart. We said the speed of the cart, the velocity of the cart was one of the controlled variables. It has to stay the same for the lab, okay? Look at anything else within the setup of that system that remained the same that could have affected whether the cart actually traveled at a constant speed or not. Okay, so any little thing that we did to kind of ensure that the speed stayed the same, or did our best to ensure that, can act as a controlled variable and must be explained how and why. Okay, in there. So we're looking for 1 manipulated variable because there's only ever one of those. Okay, in this lab, only 1 responding variable and 3 controlled variables. We always write 3 controlled variables in a lab report, okay? So because I'm quite certain I did not say that to you guys, but I know I said it in my 32 class. I'm just putting it out there that that is what I will be looking for, okay? All right, for acceleration, okay? You talked about acceleration, you learned about acceleration in Science 10, okay? Acceleration is defined as any change in velocity over time. All right, and you guys use the formula that is change in velocity over time in Science 10. We're going to look at even more acceleration formulas in Physics 20. Okay? By the end, we're going to have 5 formulas that deal with acceleration. Okay? So it won't just be the one from Science 10, there'll be 4 others. Okay? So what is accelerated motion? Any change in velocity over time. Speeding up, slowing down, doesn't matter. Okay? We're talking about any change in velocity. Okay, we're going to look at the relationships between change in velocity, distance, displacement, time, and acceleration. All right, so we'll be looking at some formulas that actually don't just contain velocity and time, they'll also contain displacement. Okay, and then be able to solve accelerated motion problems. So there's going to be a fair amount of algebra starting today. Okay, no more just manipulating v equals d over t. Now we're going to have more complex formulas that we will have to manipulate. All right, so whenever the velocity of an object is changing, okay, that object is accelerating. Remember that in physics we do not generally use the term decelerate, okay, because decelerate implies that you will come to a stop. Okay, we are not necessarily going to be doing that. Okay, so we just use the term acceleration. It's either positive or negative. Okay, now it says here the meaning of average acceleration, but I would like you guys to actually change that word, okay, in your notes package to read not average, but uniform. Okay, uniform acceleration means that my velocity versus time graph would be linear. Okay, that would mean that the amount the object is changing its velocity by is the same every second. Okay, it's doing the same thing every second. So, for example, if you were to drop something, it would accelerate uniformly at 9.81 meters per second squared. Okay, that line would be slanted, and the slope of that line would be 9.81 meters per second squared down. Okay. All right, now an example, a good example of something accelerating with uniform acceleration is if you drop something, okay, or a plane during takeoff. Why is a car not a good example of uniform acceleration? If you're at a stoplight and you pound on the gas.
You're always a bit of human error. You might not be applying the same amount of force to the acceleration the whole time.
Okay, let's say I just mash the pedal right to the floor and hold it there. Now I can take away that human error, and it's like a racetrack, so all I have to do is point the car. Even then it won't be uniform, even if I eliminate all the human error involved.
There's a delay between pushing the pedal and the car actually moving forward.
Okay, let's, you're right. I will qualify my description again. Once the pedal is to the floor, I begin recording.
When you change gears, the car kind of slows down a little bit and then accelerates even more.
Yeah, okay? Because your car has a transmission which has gears, okay, you do not accelerate at exactly the same rate the entire time. Each gear allows you to go faster, but doesn't allow you to accelerate as greatly. So if you're looking at a velocity versus time graph of a car accelerating away from a stoplight, it starts out in first gear pretty steep, okay? And then in second gear, less steep. Third gear, less steep. Fourth gear, fifth gear. And maybe you have a 10-speed transmission because, you know, that's how cars are now. They're like bikes were when I was a kid. You could buy a 10-speed. Now people say 10-speed, I picture a bike, but it's actually a car. Okay? You can get a 10-speed transmission, or you can get a continuously variable transmission that is constantly changing the ratio of the gears. Okay? So there's differences, but the fact of the matter is your acceleration still looks like this, because as you go faster, your transmission and engine simply cannot keep up that rate of acceleration. Okay? Even an electric car is still not going to be as uniform as a plane. Okay? And the reason for that is an electric car is still going to have some sort of gearing that is allowing it to accelerate, okay? But it's going to be much more uniform because it's not going to gear up like a combustion engine. For a plane, planes don't have gears other than a landing gear, which has no effect on this part of the thing that we're talking about. Okay? You just push the throttles forward and the engines just wind up and push. Okay? So your acceleration in a plane is much more uniform for that reason. To a point, obviously. Okay? As you approach your maximum speed, you're going to flatten that curve out a bit. All right, so uniform acceleration, which is what we're going to deal with most of the time, is going to look like this. Okay? Very rarely are we ever going to deal with anything that isn't uniform in terms of acceleration. All right, so this is the formula that you learned last year. A equals VF minus VI over T, or as it appears on your formula sheet, change in velocity divided by change in time. Okay, now, where does that formula come from? Oh, nobody roasted me. I was waiting for somebody to say the formula sheet, because that would have been a good answer. Okay, where do we derive that formula from? From that graph. Okay, on the y-axis, we have velocity. On the x-axis, we have time. If I calculate the slope of this line, I'm going to have m equals y minus b over x. The y values would be my final velocity, my initial velocity. And what's on the x-axis? Time. Okay? When I translate that formula to what's actually on that graph, that's what it comes out to. Okay? It's calculating the slope of a line on a velocity versus time graph. Okay? That's where we get it from. Okay, questions there so far? Where we get that one from? All right, so suppose we have the plane in this picture, okay, and it starts from rest. There's some terminology we have to be mindful of when we're talking about acceleration. If something starts from rest, its initial velocity is 0. Because if you're at rest, you're not moving. What if a question says an object comes to rest?
It's stopping, slowing down.
Okay, what's its final velocity then?
0.
0. Okay, so little things like that. They're word clues that don't actually give you a real number. Okay? All right. It accelerates down the runway, and after 29 seconds is at a velocity of 72.2 meters per second, where the plus sign indicates the velocity points to the right. Okay? Determine the average acceleration of the plane. All right, so for this question, we would use the formula we learned last year, because we were given the final velocity, we were given the initial velocity, and we were given the time. Okay? So we can just plug those numbers in and solve. So that would be 72.2 minus 0 divided by 29. Okay, so this plane is accelerating at 2.5 meters per second squared. How did I arrive at those units? What units did I divide here?
Meters per second by seconds.
I divided meters per second by seconds. So imagine that these are fractions. Meters over seconds divided by seconds, which is the same as saying seconds over 1. Everyone all right with that? When I divide fractions, how do I do that? Reciprocate and multiply. Okay, so when I reciprocate this, I'm going to have 1 over seconds. What's meters times 1? Meters. What's seconds times seconds?
Seconds squared.
Seconds squared. Okay? The other way you can look at this is if I divide meters per second by seconds, I get meters per second per second. In other words, the rate at which I change my velocity. If something is falling, it changes its velocity by 9.81 meters per second every second. Okay? We just say it meters per second squared because mathematically that's how it works out. Okay? But it actually means meters per second. Okay? It's the rate of change of velocity. All right, everybody okay with that? Looking familiar? Okay, you definitely would have used that formula last year in Science 10. Okay. Yep, so that's the math that we just did there. Okay, these are our other formulas that we're going to be using. Our other acceleration formulas. They are all on your formula sheet, so you don't need to write them down. Okay. The first one we're going to use, okay, is d equals, so d would be either distance or displacement depending on whether you're given vectors. Okay. Displacement equals initial velocity times time plus 1/2 at squared. Okay. Now, here's where that formula comes from. We learned about velocity versus time graphs the other day. Okay. If I have a velocity versus time graph that looks like this, how do I calculate the displacement?
What's underneath the line?
Right. I calculate the area underneath the line because that's essentially going average velocity times time. It's doing this, right? Okay. Well, under this line are a rectangle and a triangle. Okay? This is times 0 right here. So this would be my initial velocity. Agreed? Okay. So if I go base times height, am I taking initial velocity and multiplying it by time? I am. So this calculates the rectangle. The 1/2 at squared part calculates the triangle. Okay, it's kind of, it's that 1/2 base times height kind of thing, but it's just changed a little bit to actually use the slope of the line. Okay? So this calculates the triangle. Right? So if I have 3 out of the 4 of these, then I can solve for D. Okay? All right. Its partner here looks very similar to it, except it's VF times T minus 1/2 at squared. Right? So what that's saying is, here's VF up here. So if we go VF times T, okay, what it's essentially calculating is this whole box. And then it's subtracting this triangle, because this triangle and this triangle are the same. Okay? So if I calculate the area of this whole box, and then I subtract this triangle, I am still also left with the area under the line. Okay, that's where that one is derived. Okay. This one here, not really derived from graphing so much, but it's an important formula, especially when we get to projectile motion later, okay? And it has the knack of not requiring what variable in it? Time. Okay? So that's why this one's not really derived from a velocity versus time graph. There's no time in it, okay? It's just relating displacement, acceleration, and the change in velocity, okay? These velocities do have to be squared when you are using that formula. It's something to watch out for. Okay, and then our last one is this one here. We don't use this one very often, okay? And it does absolutely have to be a uniform acceleration situation for it to work, because if I take VF and I add VI and I divide by 2, what am I calculating?
Acceleration?
Nope. I have two things. I'm adding them together and then I'm dividing by 2. What am I calculating? The average velocity, right? So all this formula is d equals average velocity times time. That's this. Okay, it's really just that formula, but it takes into account that the velocity is actually changing and not constant. Right? So we don't use this formula very much, okay, in acceleration, because we don't like to use a formula that's about constant velocity when velocity is not constant. Okay? Just kind of not something we use very often. All right, so those will be our new formulas, and what we're going to do today is go through how to manipulate each one, go through some practice problems for each one, and then give you guys some time to kind of just work with them, okay, so you get the hang of using them, because these formulas will be the bread and butter of both Unit 1 and 2. All right, questions so far? All right, to have you write this one down, and write this problem down, and then we'll walk through it together. Okay, so in this question, what's the first thing I should do?
Write down all the things you have, okay?
Yeah, write down all your givens. You have 5 possibilities for a formula that you could use for an accelerating object. If you write down your givens, it becomes pretty easy to figure out which formula you have to use. Okay, and you get a mark for it, so it's totally worth your while. Okay, so a hybrid car with an initial velocity of 10 meters per second east. What did they just give me? The initial velocity. Okay, so initial velocity is 10 meters per second east. Okay, and the way I can tell that is, it was, well, it basically said it's the initial velocity, but it also had the right units for velocity. It was in meters per second. Okay, and they gave me the direction, east. Accelerates at 3.0 meters per second squared east. What did they just give me there? The acceleration. Okay, how long will it take? What am I looking for? Time. To reach a final velocity of 25 meters per second east, so that's VF. Okay, what formula should I use? Well, 4 out of the 5 formulas have displacement in them. Can I use any of those? So they're all out. All the new ones are out. This one uses the one you're familiar with. Okay, I have VF, I have VI, I have A, and I'm looking for T. That's the formula I would get to use here. All right. Right now, that formula solves for A. I want T, so I have to manipulate. All right, so T is on the bottom over here. How do I get it over here?
Times it by T.
Right, multiply both sides by T. So T is going to cancel, T is going to come over here, and then I need to get T by itself, so what do I do with A? Divide both sides by A. Okay, just following the rules of algebra. All right, so t equals then 25 minus 10, okay, because my final was 25, my initial was 10, and that took, and they accelerated at 3 meters per second squared. So 25 minus 10 is 15. 15 divided by 3 tells me this is going to take 5 seconds. Okay. So here's where the marks would be for you in a question like that. 1 mark for your givens. You get 1 mark for picking the correct formula. You would get 1 mark for your manipulation, your algebra. And sometimes, I'm feeling generous, I give a mark for plugging in the numbers correctly. Okay? And then 1 mark for your answer. So this would be between 4 and 5 marks. Okay? All right. Let's look at the other manipulations for this formula here. Okay, so we already know it can solve for A. We just did the manipulation to solve for T. What if I wanted to solve for VF? What would I move first? Time, because it's not attached to VF. Okay, so I do the same thing I did before. I'd multiply both sides by T. All right, now how do I get VF by itself? Add VI, right? Do the opposite. Right now I'm subtracting VI. So VI plus T times A equals VF. Okay, now, just so that we're clear here, T times A calculates the change in velocity, right? T times A is equal to VF minus VI. One second. Okay, so it calculates the change in velocity. So when I move VI over to this side, I'm saying the initial velocity plus the change in velocity equals the final velocity. That should make like logical sense, right? Not just mathematical sense, but logical sense. Sorry, question.
So how do we get positive VI by itself?
Just about to go over that. Stop reading my mind. Okay, yeah. All right, so if I want to get VI by itself, okay, I would say I go all the way to this same manipulation. I do everything the same. I move VI over here, and now it's positive. What do I do with T times A to get this over? Just subtract T times A over to the other side. And here's why that is going to logically make sense. Okay, so now I would have VI equals VF minus T times A. Remember, T times A calculated the change in velocity. So if I take my final velocity and subtract how much it changed by, that should tell me what I started with. Okay, does that make sense kind of logically for us? Okay. All right, so those are the manipulations of that formula. Here's the one thing I'm going to caution you about, because sometimes people do this. As I'm going through all the manipulations, they're writing all the manipulations down on their formula sheet. That's not going to help you later. Okay? You're not going to get to use your formula sheet on a unit exam or a final exam. So you have to learn how to do algebra. Okay? Just writing down all the manipulations is A, going to fill up your formula sheet really fast, okay? And B, not work in the long run. All right? So you've got to learn to do that algebra stuff. Okay, these 2 questions use that formula. I'll give you a little bit of time to get them done. Yes? Yeah. So for number 1, okay, we have a motorcycle with an initial velocity of 6 meters per second east. So they told me what VI is. Okay. Accelerates at 4 meters per second squared, so that's the acceleration, and it's east. Okay, how long will it take, so this is the same as the example we just did, okay, to reach a final velocity of 36 meters per second east? So obviously I'm looking for time. I have the other 3 things that are in this formula here. Right, so that'll be the same manipulation as the example we did. We'll multiply both sides by T. We'll divide both sides by A, and we'll be left with that. Plugging in our numbers, we're gonna have 36 minus 6, okay, over 4. Right, so 30 over 4 should give us 7.5 seconds. Okay, questions on that one? How many people are done number 2? Okay, do you just need a little bit more time, or are we stuck? Okay, I'll give you another couple of minutes and then we'll go through it. Okay, so on number 2, we have an elk moving at a velocity of 20 kilometers per hour. From the context of that question, that sounds like it's the initial velocity to me, but it does need to be in meters per second. I'm gonna have to convert it back to kilometers per hour when I do the final, but for right now, for my math purposes, I do need it in meters per second, so I'm gonna divide it by 3.6. Okay, so that's gonna give me 5.5 repeating. Meters per second north. Okay, it accelerates at 1.5 meters per second squared. Also north, okay, for the next 9.3 seconds. We are looking for the final velocity of the elk, okay? So when I look at this, I can see that this is the formula I'm going to have to use because I'm looking for VF. I have acceleration, initial velocity, and time. All right, so I need to manipulate for VF, which is going to mean I move T first because it's not attached. Then I will add VI to both sides, and that'll solve for VF. Okay, when I plug in my numbers, that's going to mean the 5.5, okay, plus 9.3 times 1.5. Okay, now a caution for you here, or a tip for you here. In terms of getting the right answer with the right number of significant digits and all of that good stuff, keep all of these, okay? Do not round off any numbers in an intermediate calculation. Keep all the decimals in your calculator, okay? And don't round off until the very end. Okay, because we have to keep all of those for the sake of accuracy. So I'm just going to use that one, okay? Just have the answer there with all the decimals, plus 9.3 times 1.5. All right, so that's going to give me 19.5. The question only has 2 significant digits, but I'm not done because that's in meters per second, and they wanted it in kilometers per hour. So instead of dividing by 3.6, I'll multiply by 3.6. And I get 70 kilometers per hour. Okay. Now, just so you're aware, I cannot remember the last time I gave a question on an exam where I made you do that conversion. Okay. Now, I do occasionally give a displacement in kilometers and a speed in meters per second. I will admit to doing that. Okay, but that's a much easier thing to remember how to do because it's just 1,000. Okay, but I don't generally do this, especially not twice in one question. Okay, it's kind of pointless. All right, I want you guys to copy that one down, write out your givens, and see if you can figure out which formula you're going to need for that one. And then we'll walk through it together. Okay, so in this question, we have a cattle train traveling west at 16 meters per second. All right, so we know that the initial velocity is 16 meters per second west. And it's brought to rest. What does that mean?
Final velocity is 0.
Means final velocity is 0. Okay, and that's done in 8 seconds, so that's my time. All right, assuming uniform acceleration, and I don't have the acceleration, okay, find the displacement. So that means I'm looking for D. All right, what formula do I have that's got VI, VF, and T, and will solve for D without acceleration?
Oh. Is it?
Is equal to VF
Exactly. Okay, this one, the one I told you, it has to be uniform for this one to work. Well, they specify in this question that the acceleration is uniform, which means I can use that one. Plus, it's the only one that matches with the givens I have. I don't have acceleration. This is the only acceleration formula that doesn't have acceleration in it. Okay, so I don't have to manipulate it. That's good news. I just have to plug in my numbers. Okay, so we'll have 0 plus 16 divided by 2 times 8. So 8 times 8 should be 64 meters west. Okay, the displacement's a vector quantity, and they did specify they wanted the displacement. Okay? Everyone all right with how that one works? Okay. If I want to manipulate this formula, let's say I want to solve for t. How do I get t by itself?
Oh, divide everything by
Actually, you're right.
Oh.
You said you wanted to move the whole set of brackets over? Absolutely. I can do that. Remember, the brackets mean I have to do that first, right? Okay, according to order of operations, that whole big mess that's in brackets is like x. Okay, it's all going to be done first anyway, so I can just move it over all at one piece. Okay, so I would just have d divided by vf plus vi over 2. Remember, this actually just calculates average velocity. Last time I checked, that was true, right? d over v equals t. That makes sense. Okay. All right, what if I wanted to solve for any of the things that are in the brackets? So let's say I want to solve for VF.
Would you have to square root it to remove the, or not square, never mind, right? Sorry, I thought that was a square root.
No, that's okay. If it was a square root, I would have to square everything. Okay, but it's just brackets. I want to solve for something that's in the brackets, so what should I do with t right now?
Divide it.
Yeah, I gotta get rid of t. Once t is gone, is there any need for the brackets anymore? Okay, perfect. So we'll divide both sides by t. Hey, this looks familiar. Right? Isn't average velocity displacement over time? Okay, so we're on the right track then. Okay, so now that I've done that, now I no longer need the brackets. T is gone. Okay, I want to solve for VF. What do I do with the 2?
Multiply.
Multiply both sides by it. Okay, so now 2 is over here. What do I do with VI? Subtract it. Okay, so I would have 2 times d over t plus vi equals vf. If I wanted to solve for vi, switch those two and you're good. Okay? Everybody all right with that one? Like I say, we don't use that one very often. Okay? We still have to know how to use it, obviously, but we don't use it very often. Okay, those two formulas, or sorry, those two problems use that formula. Right, give them a try. Okay, and hopefully we'll get a chance to go through those before the bell goes. I just want to quickly look at number 2, because number 2 has an important thing that we have to be aware of to do with vectors. Okay, so the ball moves up the hill with an initial velocity of 3 meters per second. Okay, so VI, that's equals 3.0 meters per second uphill. Okay, 4 seconds later, and this is like the worst thing ever. How many significant digits in FOUR?
4.
I have no idea. That's not how you write numbers. That's why one of the reasons we don't use this textbook. Okay, 4.0 seconds. I'm just going to write that. Okay, and it's moving down the hill at 9 meters per second. Okay, mathematically, how do I represent uphill and downhill? Positive and negative. So when I do this, I'm going to have negative 9 plus 3 over 4. Okay? So when I do that, negative 9 plus 3 is going to be negative 6. Okay? Divided by whoops, sorry, I did that wrong. Divided by 2, okay, times the time, which was 4 seconds. Okay, so negative 6 over 2 is negative 3 times 4 seconds. Is giving. They've got this written down before you pack up. Would I give you full marks for this?
No,
And why wouldn't I?
there's no direction.
Yeah, the question didn't give me positive and negative. It gave me uphill and downhill, which is also, this seems really sticky, different than up and down. That's up. That's down. Uphill is like this. Okay? They are different directions. If it says uphill, your answer needs to be either uphill or downhill. Okay? Just so it matches. I know that's really, really sticky, but that's physics. Okay? We'll continue working on acceleration tomorrow. If you have questions about your lab report or want me to go over it, make sure you pop in at lunch or nighttime or after school or whatever. Oh, not after school today. I have to leave after school today. Okay? But you can come in and see me at nighttime or at lunch.